Myself and my former colleague, Mike Standish, is going to talk to you today about software testing. We haven't got any silver bullets or even bronze bullets in terms of the actual testing solution. This presentation is a very quick walkthrough where we are in terms of software testing today compared to where software testing was with the Myers art of software testing back in '79, and also looking at the key issues and challenges we face today in terms of actually advancing technology, in terms of multi-core machine learning, etc. If we go to the next slide, just some very brief disclaimers. I'll not go through them in detail. These slides have been generated by myself and Mike. They are our personal views, not endorsed by Atkins or UK MOD. Next slide, please, Mike. You are free to use any of the contents if you so wish to, but please just reference it accordingly. Next slide, please. And again. As I said, we do not answer the actual fundamental question in terms of where are we today in terms of V&V. We do not have just one technique which will solve anybody's solution, but we highlight some of the actual key issues around software testing, things like effectiveness and reliability of the testing technique. Effectiveness is the ability of the technique to find faults. Reliability of technique is that it will detect no faults, reliable every time you use that technique. And while standards play a very important role in providing us a prior belief before we release that software into the field, standards are always, and unfortunately, always behind the technology. And I think that one of the actual key messages we are saying today, the complexity of our software systems and the technology advances outstripping our qualification understanding. Next slide, please, Mark. As I alluded to at the start on this presentation, the art of software testing by Myers back in '79, while it was almost the state of the art back in the late '70s, it is still often referred to, and even today, it is part of numerous undergraduate and postgraduate courses. And I think perhaps the message we'll repeat during this presentation is that while those software testing techniques are dated, and software testing research haven't truly advanced 41 years on, and they are still quite relevant today, trying to meet the many challenges we actually face. And as I alluded to there, or in the earlier introduction, the actual complexity of our systems, not only with the lines of code, but multi-core machine learning, artificial intelligence, big data, digital twins. And there are quite a lot of systems where we need to start thinking about how best we test these systems instead of using one or two techniques. We need to bring engineering judgment to bear when we come to test our systems and move away from perhaps what numerous standards tend to mandate. While some of the standards used to mandate, for example, 55 issue 2 in the defence world used to mandate the use of formal methods for safety critical software. On the whole, the defence domain have moved away to software assurance using process and certain techniques as defined in 178B and C, while other niche markets still rely on formal verification, as Paul in the introduction said, our guest speaker also indicated. There are, green shoots in terms of formal verification starting to be used for very critical functions or safety critical security functions. And I think that last bullet point on this slide is that we tend to see testing as an inconvenience to payment by project managers. Software testing is about finding defects, and any software tester should be encouraged to find defects. While some perhaps in the actual project management see software testing as a hurdle to final release and acceptance and payment, we should remember that software testing is about finding bugs and providing us a level of confidence before we actually release the software into the field. Next slide, please, Mark. As we already alluded to, standards do provide a level of guidance and best practice, but unfortunately they do lag behind the technology. A good example on this is multi-core. If we looked at multi-core, it's been around for over 2 decades. But if you look at where the actual civil guidance in the airborne domain was, CAS 32 came out in 2014, and that was only guidance and not mandated. So, we need to try and be more proactive in looking at how best we apply software testing and the different number of software testing approaches to meet our advances in technology, because we cannot afford just latency, because these systems of machine learning, AI, will be used in the field, and we need ways of providing levels of confidence and assurance into these new developments. And I said guidance do play a part, but they are struggling and they're not keeping pace with the actual emerging trends. Next slide, please, Mark. And I'll come back to this concept about effectiveness and reliability. It is not new. Good Enough and Good Heart in the late 70s came about. These need to elements or properties in terms of looking at software testing in terms of effectiveness and reliability. There is no point in using a software testing technique if it is ineffective in finding faults. And back in the late 70s and the early 80s, up to the mid 80s, there was a small number of empirical studies which did try and examine the effectiveness of software testing techniques, and these came up with that no single technique was actually effective, and it was only applying multiple techniques, things like code inspection, structural coverage, i.e. statement and decision coverage, and dynamic functional testing maximize the actual fault effectiveness of these approaches. And in some ways, that's what a number of these standards we now commonly use today, things like 178B-C, try and do through the development lifecycle from the requirement, design, and also code and test. So the next slide, please, Mike. Now, in the armory of the test them, there are a number of techniques which we can apply, either statically or dynamically. This slide show a number of techniques which could be applied depending on the type of system you are testing against, or in a number of cases, it dependent upon what the software testing you use state in the actual software standard. But I think, again, this goes back to what I said earlier, that we need to bring engineering to bear to the software testing challenges. We need to move out of what the standards mandate, while it is best practice, or it was best practice. If you look at 178B-C, 178B was released in 1992, and fundamentally 178C, which was released more recently, still used the same software testing strategies. So I do think it's time to bring in engineering judgment to bear when we come to look at software testing techniques. While Myers recommended numerous software testing techniques, on the whole, we always fundamentally go back to the same approaches. And also, if you look under the dynamic testing there, you've got boundary value analysis and equivalence partitioning. Now, while we all use equivalent partitioning to prune out our test cases, we'll have a valid and invalid set of test data. And when we assume that we don't need to test all the different data elements because they'll all behave the same, that isn't always the case. So if we are going to make software testing arguments, we need to use a claim argument-based engineering judgment. Next, please, Mike. Right, I'll hand over to you, Mike.
Okay, thank you very much, Mark. Yeah, so Mark's already spoken about some of the challenges to the reliability and effectiveness of some of the testing techniques, but there are also the actual technical approaches such as AI, machine learning and digital twins, for example, that those testing techniques are to be applied to. So we're very much in an evolving technological world, and therefore we also have subsequent evolving testing challenges, if you like. So there may be trouble ahead, but it's already on our doorstep, in effect. So this section is just going to provide an overview of some of the technical concepts which have the safety assurance testing challenges. So the concept of digital twins isn't new, but how we wish to exploit the technology with true automated data flows between the digital and physical objects is, and how we use these in more and more critical areas, both from a safety and mission perspective, means that our assurance requirements must increase accordingly. So we need to ensure that digital twins will make the right decisions based upon the fundamental and core algorithms, and also that the decisions are based on the right data, so confidence that we tell it the right things. And our efforts to understand the safety risks and the assurance of digital twins, so there's a work of Kevin King from BAE with York University, which is a welcome addition to the field. But with any safety principles, such as the clarity around safety-related goals, how are these fundamentally tested within the software, and what part does software play in adhering to these principles? And for confidence in a digital twin, like many systems, it's fundamentally driven by the data properties such as integrity, consistency, and accuracy. And there are also the dependability properties such as reliability and availability, if we're going to exploit the automated data flows of a true digital twin. So how do we sufficiently test to uphold any of these data properties, for example? And of course, there are also the issues of cyber attacks and the risks that are associated with complicated infrastructures and the connectivity challenges, especially with real-time systems. So how do we build the software and test such devices? That needs to consider the safety and the security implications from the outset, which is of course an ongoing challenge. Another area which has numerous software safety assurance challenges, if we're going to fully exploit the technology, is obviously that of AI and machine learning. So, as expected, with a technology with such huge potential, there's a great deal of research ongoing in terms of gaining that V&V assurance of such techniques. However, there are still substantial challenges to overcome if we wish to fully exploit the technology. So at present, the solutions which adopt AI and ML find themselves subject to various weaknesses which could be exploited from a security perspective, or could manifest themselves as risks to safety. And part of this process is to perform sufficient software testing to understand and to mitigate this. So for example, how do we design for ensuring that adversarial data poisoning will not pose a risk where the integrity of a model is threatened by introducing poisoned data into the training data set? Do we test that at the design stage? Do we test for its detection? Or do we test to ensure that a model can unlearn, for example? And how do we test for effective and assured methods for structured and unstructured pruning of the training data, for example? And obviously, data integrity plays a huge part in this as well. So testing that the data is correct, true, and unaltered. And at present, we currently use a layered approach to verifying traditional software. So different testing aspects of software from different levels to provide the assurance that we require. But what are the equivalent levels for AI and machine learning, for example? And challenges such as these are part of current thinking and current research, but are we at a level to sufficiently test and assure these? And the key part to this, an underpinning part to this, is the question of when is enough. So what criteria do we use to satisfy ourselves that we have sufficient confidence? Is this based upon our old understanding of what good looks like, such as MCDC, or do we look at new measurements? And part of this is bound in the problem space, which isn't an easy task in itself. And of course, there are the technologies that are related to the IA space, such as neuromorphic engineering and quantum computing, and designing the optimized hardware for AI as well. So this introduces additional considerations such as the software and hardware integration challenges. And as we move further forwards with implementing the AI and ML, for example, we're going to have to take additional steps to understand the technology and also learn about how to assure these systems. So we need to take these baby steps to gain this confidence. And part of the near-term solutions and the mid-term will continue to adopt the sort of traditional software, the type that we have today, and we'll have to learn how this interacts with the AI and the ML, and how we integrate this software is crucial to how the integration takes place. And this has its very own assurance challenges in itself. So as we've spoken about, really, in the immediate future, we'll have this mixed bag of implementations, which includes the advanced technologies and the more traditional software. And as we continue to learn about the technical implementations, we also continue to gain trust in these solutions. And this trust isn't binary, as that image tries to show. So for various software solutions, be it bespoke or COTS or MOTS, there'll be grades of understanding and assurance trust. So as we learn more, this trust will increase. However, due to this mixed bag approach, the interfaces will continue to be key. And with the move towards more complex implementations, such as machine learning or AI, our ability to fully understand and test the solution will become much more limited. So what's the sweet spot between the satisfactory exploitation of an approach and having sufficient trust? And that may be based upon a limited understanding, certainly in the first instance. So as are we moving to an initial near state of zero trust for safety assurance, for example? Are we starting from a position of mistrust and then building the subsequent confidence from this? And there's work in this area, but none of it's definitive. So there's a work of Rushby, for example, who has some applicable concepts on gaining prior assurance and the confidence within models and their actions. And there's also work in this area from Heriot Watt University and DSTL looking at utilizing deep neural networks to develop safety frameworks for critical systems. So again, that's a good premise, an excellent premise, but not conclusive. And so traditionally, we have the relevant security environment is quite dynamic. It's got rapid and evolving threats. Therefore, there is a perpetual mistrust, if you like, or an ability to withstand and respond to threats. So the question is, could this be the case from a safety assurance perspective with a consistent mistrust of the underlying software solution, but with interfaces or wrappers to inhibit or limit certain aspects of the software to allow that trust to be gained? And as I said, the persistent problem with this is the interface. And the interface is sort of a root cause to some of these challenges. And this could be with the traditional, dare I say it, 178C compliance software in the air domain with functional cores that are implemented with machine learning. Or, for example, it could be with neuro-symbolic learning, NSL, with the use of deep learning neural network architectures and the use and combination with symbolic reasoning techniques. And with these, there's a need to ensure that the outputs from these advanced techniques are bounded, and that's perhaps with the use of inhibitors, for example. So there are quite a few challenges to these approaches. Some are the subject of active research, whereas others require sort of further analysis, and the solutions to these will drive the software design decisions. And they're also based upon the context to how that system is used, and also, crucially, the ability to perform sufficient testing. So with that in mind, I suppose the question is it time to refresh how we currently approach these problems? So seamlessly, I'll pass that back to Mark.
Right, thank you, Mike. Do you go to the next slide, please? And the next one. I think we covered a bit earlier on a number of software testing techniques. And again, it go back to the actual type of system and the test. Is it safety critical? Is it security related? Etc. And you need to select your software testing strategy based upon the leveling of security and safety required. Some of these techniques here, also stated in Myers, we sort of very briefly touched upon things like equivalent partitioning, domain-based testing, system testing, and also mathematical proofs for program correctness. So if you go on to the next slide, Mike, please. And it go back to, we need to understand better what these software techniques provide us in terms of what confidence is it providing us in towards that arguments, before we actually release that software into the field, even in terms of safety and security. What does good look like for our systems under test? I would argue that back in the 70s and 80s, when Myers was writing his work, it would often assume you use one technique or only 2 or 3 techniques to provide you with the level of confidence required. And I think we need to move away from that. We need to think about how do we make that claim, argument, judgment that software is now ready to be released into the actual system and into the actual field, and that total argument, as Mike was saying there, in terms of the integration testing and the build up of evidence to give you that final argument. And are we moving into a field of more solid box testing and moving away from sort of structural coverage due to the actual complexity in terms of our systems? Some of our airborne systems now are now exceeding 5 million lines of code. And the economics of software testing are making it infeasible to do some of these software structural testing techniques we had done before, like MCDC coverage, for example, because of the time and cost, and we need to get these systems into the field. So where with that economic equilibrium in terms of software testing technique to provide a maximum use of our resources and providing that maximum level of confidence. And I think, you know, now 2021, we you know, how many systems we actually still see today we use manual test cases when, you know, we can start using test automation, which provide great opportunities to do stress testing and statistical testing, reliability, etc. And we can do these runs overnight, automatically, and you know, it removes that actual regression testing argument, which I know we not touched before during the presentation. Can we move on? Next slide, please, Mike. As I sort of just mentioned there, surely we need to be looking at as much automation as possible, and also test automation also give it the opportunity to test these new advances in technology, you know, in terms of digital twins, machine learning, AI, etc. But also, it, you know, if we are trying to gain a statistical figure for our software testing reliability, then it does bring the possibility of doing statistical testing and providing us with a statistical reliability figure. And then Mike alluded to as well, you know, interfaces and integration it perhaps key to, as our systems get larger and larger. You know, now, you know, integration testing isn't new. It's been around a long time, but we do it poorly, either in terms of software hardware, and looking at how our standalone systems interface with other systems. I think there is something there in terms of design by contract and formal specifications would certainly help in that area. And in terms of the actual software testing techniques, looking towards the actual future in terms of AI, ML, and DTs, what metrics do we need to consider for actual success? You know, what is the stop testing criteria? You know, one of the reasons why we use statement branch and MCDC coverage in 178 B and C is that we all know when we can stop testing. You know, as a community, we do need to know when we can stop. What you know, because we can use it as a good enough indicator. You know, these systems, you know, we need to understand when is enough is enough. And that goes back to that earlier point I made as well, where in that economic sweet point to determine the best use of our software testing resources to make sure we have found the actual faults and the diminishing return of doing more and more testing. And perhaps we really do need to reconsider the actual best combination of software testing techniques to provide the effectiveness and reliability. Next slide, please, Mark. And again, please. And I think I covered this first bullet point already. Some of our legacy software testing techniques is the economics of using them is actually preventing them from being used currently. MC/DC coverage, for example, the time and expense of doing MC/DC coverage for millions and millions of lines of code is expensive and time consuming. And is that maximizing our actual time and budgets to maximize the actual testing? You know, could we be using other alternative software testing techniques which will provide us with the same level of confidence, if not more so? And what does coverage really mean in terms of machine learning and artificial intelligence or systems? I don't believe we have got a measure of coverage from these systems yet, and I know there have been research in this area by York and others, but currently I don't believe there is actually consensus about what would coverage look like for machine learning and AI. And have we put too much faith in these software testing techniques we use on a daily basis? Is it based upon just legacy use, or is it based on empirical evidence and our own domain knowledge? You know, is it worthy to be carrying on using these techniques just because we have used them for the last 41 years? You know, when I first got into computing back in 81, I was using a VIC-20. We no longer use that level of computational power and Commodore Basic to actually program our programs today. But the software testing techniques have not truly advanced beyond Myers back in '79. And as I alluded to slightly before about what do we need to do for AI and machine learning compared to our traditional software development code bases. In the short term, and Mike alluded to, a lot of the AI and machine learning will be integrated into our traditional software. You know, is it 5-10% currently? But I'll see that growing as our maturity of AI and machine learning, and how do we qualify these sort of systems to the wider use in the safety critical world. And I think Paul going to intervene any moment to tell me to hurry up, so I'll be very quick, Paul. And we need to go back to engineering approach and perhaps look at how best we actually do test AI and machine learning systems. Next slide, please, Mike. And I think I covered the majority of these bullet points in terms of we need to look at effectiveness and reliability. And while standards are useful, they are often out of date, and we need to think of the bigger picture in terms of software testing techniques we are applying. And next slide, Mike, please. You know, testing is all about discovering bugs. Not all bugs are equal, and whatever technique you use, it will be dependent on what bugs you find. But fundamentally, not all tests are equal, but should always be useful. If you're not generating useful tests, then what's the point? And I'll end there, Paul.